Good morning, students. Our today's topic is T3 spaces. So firstly, let us define T3 space. A topological space X tau is said to be T3 space if it is regular as well as T1 space. So the space which is regular as well as T1, that space is called T3 space. For example, the discrete topological space consisting of two or more points. We already discussed the discrete topological space which contains two or more points, that is T1 as well as regular space. So by definition, discrete topological space is a T3 space. Now next we do the hereditary property of T3 spaces. It means if we take a T3 space, then its subspace is also T3. So let us take X tau be a T3 space and Y with the subspace topology tau Y be the subspace of X tau. We have to prove that the space Y tau Y, that is T3 space. Now because the topological space X tau, that is T3 space. So by definition of T3 space, this topological space is regular as well as T1. Now because this topological space X tau, that is T1 space, and we already discussed the hereditary property of T1 spaces. It means subspace of T1 space is T1. Therefore the topological space X tau is T1 implies that its subspace Y tau Y, that is also T1. Also the topological space X tau, that is regular, and subspace of regular topological space is regular. So we can say that Y with topology tau Y is regular also. So both conditions for being the T3 space are satisfied. So we can say that the subspace Y with topology tau Y, that is a T3 space. So you will have to prove the hereditary properties of T1 space as well as regular space in order to prove this theorem. Next, we do the theorem every T3 space is T2 space. Let us take a topological space which is T3. That topological space we have taken as X tau. X tau is T3 space. So by definition, it is regular as well as T1 space. Now we have to prove that this topological space is T2. It means if we take a pair of distinct points in this topological space, then they should have disjoint neighborhoods. So let us take 2 points X and Y belonging to the topological space X such that X is not equal to Y. Now as we already discussed, in T1 space every singleton set is closed. Now here Y belongs to the topological space X and X is T3 space, and therefore that is T1 also, and therefore every singleton in this space will be closed. So we can say that singleton Y, that is closed subset of X. Now because X and Y are different points of the set X, therefore we can say that the element X does not belong to singleton Y. So we have a point and a closed set such that the point does not belong to the closed set. And also the topological space is regular. So by definition of regularity, if we have a point and a closed set which does not contain that point, then there exist their disjoint neighborhoods. So by definition of regularity, there will exist a neighborhood W of the point X and a neighborhood V of the set singleton Y such that these neighborhoods are disjoint. It means the intersection of W with V, that is empty. Thus from here we can say that for X and Y belonging to X with X not equal to Y, we have obtained a neighborhood W of x and a neighborhood V of y such that these neighborhoods are disjoint. Thus we can say that every pair of distinct points in this topological space have disjoint neighborhoods. So we can say that the topological space X tau is T2 space. So this completes the topic T3 spaces. Our next topic is quotient topology. In order to define quotient topology, let us take a topological space X tau and Y a non-empty set. Let us define a mapping F from the topological space X into the set Y. This be onto mapping, and we define a collection of all those subsets of Y whose inverse image under F belongs to the topology of X. That collection we have denoted by tau double star. This is the collection of all those subsets of Y whose inverse image under F belongs to tau. Tau is the topology of X. Now we claim that this is a topology on the set Y, and then this will be called the quotient topology on Y with respect to this onto function F. Now to prove this collection is a topology, we will have to verify the 4 conditions of the topology. In the first condition, we show that the empty set phi belongs to this collection. For this we will have to find the inverse image of phi, and that should belong to the topology of X. Now let us find the inverse image of phi under the function f. Now by definition, inverse image of phi, that is phi, and phi belongs to the topology of X. So by definition, if the inverse image of a set belongs to topology of X, then that member belongs to this collection. So by definition, phi belongs to the collection tau double star. Now next we show that Y belongs to the collection tau double star. So let us find the inverse image of Y under the function f. Now by definition, because f is a function from x into y and function is onto also, so f inverse y, that is the whole space x, and x belongs to the topology tau. So by definition, we can say that y belongs to the collection tau double star. Now in the third condition, we will have to show that the collection tau double star, that is closed under arbitrary unions. So let us take an arbitrary collection of the members from this collection tau double star, and that collection we have denoted by the collection Bi, where I belongs to the index set. Let us denote the union of members from this collection by the set P. Now we are to show that B belongs to the collection tau double star. So let us find its inverse image under F. So by definition, F inverse B. Now substituting the value of B here, this is F inverse of union Bi, and this can further be written as union of F inverse of Bi. Now because Bi are the members from the collection tau double star, and by definition of this collection, their inverse image under F, that will belong to the topology of X. So F inverse of Bi belongs to tau for every I belonging to the index set. It means all these members, they belongs to the topology tau, and because a topology is closed under arbitrary unions, and therefore we can say that F inverse B, that belongs to the topology tau, and therefore by definition B belongs to the collection tau double star. And in the last condition, we take two members B1 and B2 from the collection tau double star, and we prove that B1 intersection B2 also belongs to the same collection. Now there are two possibilities, either the intersection is empty or non-empty. So if B1 intersection B2 is phi, then the inverse image of B1 intersection B2 under the function f, that will be f inverse phi, which is again phi, and phi belongs to the topology tau. So by definition, B1 intersection B2 belongs to the collection tau double star. Now, if their intersection is non-empty, it means if B1 intersection B2 is not equal to phi, then the inverse image of B1 intersection B2, that is given by f inverse B1 intersection f inverse B2. Now because B1 and B2 belongs to the collection tau double star, so by definition their inverse images under function f, they will be in the topology of X. And because tau is a topology, it is closed under finite intersections. So if we take two members from topology tau, the intersection will also be in the same topology, and therefore we can say that f inverse B1 intersection f inverse B2 belongs to topology tau. From here we can say that f inverse of B1 intersection B2 belongs to tau, and by definition of tau double star we can say that B1 intersection B2 belongs to the collection tau double star. So we have verified all the four conditions for being a topology. So we can say that the collection defined by tau double star, that is a topology on the set Y, and this is called quotient topology with respect to the function f. And the ordered pair formed by the set Y together with this topology, that is called quotient topological space. Now next we will discuss some properties of quotient topology. So first property of quotient topology is that quotient topology with respect to a function f is the largest topology such that the function is continuous. So let us take a topological space X tau and Y be a non-empty set, and we define an onto mapping from X into Y, and we define the quotient topology as we discussed earlier, the collection of all those subsets of Y whose inverse image under the function f belongs to topology of X, and this topology, that is a quotient topology on Y with respect to the function f. Now we are to prove that this function f from X into Y is continuous function. As we already discussed various characterizations of continuous functions, a function f from X into Y is continuous if and only if inverse image of every open set in Y is open in X. It means if we take a member from the topology of Y, then its inverse image should belong to topology of X. So let us take an arbitrary member B belonging to the topology of Y. Now because this topology is quotient topology, so by definition of quotient topology, inverse image of B will belongs to tau. So we have proved that inverse image of every open set in Y is open in X. So by definition we can say that the function f is continuous function. Now in the next part we are to prove that quotient topology is largest topology such that this function is continuous. So let us take another topology which we have denoted by tau triple star. This is another topology on Y such that the function f from X into Y is continuous. We are to prove that this topology is contained in the quotient topology. Then the quotient topology will become largest topology. So let us take an arbitrary member G belonging to this topology. Now because the function f from X into Y, that is continuous function, so by definition inverse image of every open set in Y will be open in X. So f inverse G will belong to topology of X. It means f inverse G belongs to tau. Now by definition of quotient topology, G belongs to the topology tau double star. So we have proved that G belongs to tau triple star implies that G belongs to the quotient topology. So we have proved that quotient topology is the largest topology such that the function f is continuous. So this proves one of the properties of quotient topology.